Hello, today I am going to be demonstrating this cache simulator by Caleb531. This is a cache simulator developed in Python and it has a command line interface. Now this cache simulator is capable of demonstrating n-mapped, n-way set associative and fully associative mapping schemes. Now the way this simulator works is that it has a command and it has some command line arguments which are cache size. Here you provide the size of the cache. It is not defined, but I think it's probably in bytes. And then the second argument is number of blocks per set. And this here will define the associativity. Now for two-way associative, we will provide 2 here. It means that each set will have 2 blocks, or as in this case here it is provided 3. So it is 3, it is a command for 3-way set associative with mapping scheme. Now the next argument is number of words per block, mean how many words each block will contain. Now here it has it has 2 words per block, and at last the word address argument is given, which uh, which is the words that will be provided to the cache simulator, and the cache simulator will demonstrate whether each word is a hit or a miss in this cache. Now this is the output that the cache simulator will display. Now it has some columns and some values against the values we have provided it earlier. Now here the first column is word address, which is the addresses we provided to the cache simulator. These are the addresses which are required by the microprocessor, and it will be checked against the cache whether they are present or not. So such a scenario is being simulated by this simulator. The next column is bin adder, binary address. So these are the addresses which will be generated against each of this word address, and will be checked in the cache whether they are present or not, whether it's a miss or a hit. Now, the binary address is broken down into these segments: the tag, the index, and the offset. The tag is used to check whether a block is present in the cache or not. The index is used to check the set. The index is actually of the set that in which set that block is present, and within the block at which address the uh, word is present, the word which is to be fetched. So this is referenced by the offset. And then here at the last column is hit or a miss. So it is demonstrating if the fetched element created a hit or a miss in the cache. The creator of this program has provided this package on pip, which is a package manager for Python, and you can install this package using this command, provided that you have pip and Python installed. So the prerequisite for this program is that you must have Python version 3.4 or above. So here we can see there are some optional parameters available as well. For example, like here num adder bits, which stands for number of address bits. So the number of address bits are the number of bits used to reference a memory. So here it says by default the largest fetched element will decide the number of bits in default case, or we can provide it ourselves. And here another command line argument is replacement policy, which is the eviction scheme for any cache. Most common is LRU or MRU. There are other schemes as well. Now I have already installed this package using pip command. I have pip in Python installed. Now I will demonstrate this simulator on my personal computer. Now here I have an environment, WSL environment, Windows Subsystem for Linux environment running Ubuntu 20.04, and I have installed this package inside it. Now the package was not globally added to the part, which means I cannot run it from anywhere. So I have to navigate to its directory where it's installed and have to run the commands. Uh, Now for today's tutorial, we will be running some commands which will demonstrate direct map, fully associative, and two-way associative cache schemes. Now, particularly, we will be running programs which will simulate environments like all hits in a cache, all misses in a cache, 50% hits in a cache for each of these mapping schemes. I will be now running this command which simulates a direct map cache scheme and produces all misses in a cache. Uh, so I will just copy this command and paste it into the next terminal, and by hitting enter I will run it. So here you can see other than the compulsory miss, all of the cache elements were a hit. Now how I did this, I will be walking you through the command and the command line arguments. So, and the command is cache simulator, and it has these requirement and some optional command line arguments given to it. So the cache size I calculated is 256. For this project, I was required to calculate a uh, cache size based on this formula, which included the last two digits of my roll number, adding 10 into it and multiplying it with 12. Now this generated a cache size of 252 for me, so I just rounded off to 256 as memory is usually represented in powers of 2. So if I do 2 raised to power 8, it creates a 256. So the next argument is number of blocks per set. So in direct mapping scheme, each set has only just one block. The next argument is number of words per block. So I have chosen it to be 4. Means that wait, let me just so as I was saying, I have chosen it to be 4, so each of my block will have 4 words in it. And the number of address bits mean the total size of the memory will be addressing will be used for which will be using 11 bits. So if I do 2 raised to power 11, it creates a 2004 8. So I'll be referencing, so in this case, the simulator will be referencing a memory of 2048 bytes. Now, at last, the last argument is word addresses. So I have given it addresses 01230 Now, these addresses created all hits because when the first element was fetched from the memory, it was a miss. We call it as a compulsory miss. And the cache is initially empty, but after fetching this first element, the uh, next four elements were fetched into the cache. As the number of words per block is 4, so at a time we can fetch 4 elements from the memory. So afterwards, the next 4 elements, when referenced, all created hits. So this was a scenario in which the cache will create all the hits other than, of course, the first when referenced. Now for the next scenario, I will be running a command which will simulate all misses in a cache. Let me just copy this command and clear my terminal, and I will paste this command in my terminal and execute it. Now as you can see, the cache created all misses. So again, looking at the command, we have same cache size, same number of blocks per set, directly mapped cache scheme. We have same number of words per block for same address bits, but we have different word addresses. Now, as at a time the four elements are fetched into the cache, so I have provided addresses which are four elements apart for this example. As the addresses goes like 0, 4, 8, 12, 16, which are four elements apart. So at every element fetch, it fetches the next corresponding four elements, but in this case, at each cycle, elements which are being fetched are four cycles apart. So it creates a scenario where there are all misses in a cache. Now this depends upon the number of words per block. Now for this next example, I will be running a command which will demonstrate 50% of hits and 50% misses in a cache. So let me just copy this command clear up my terminal and paste it in the terminal and execute it. Now for this case I have used 11 memory addresses as the first will be a compulsory mess, and after that the scenario will be correctly identified as 50% of hits and 50% of misses in a cache. So here I have simulated this environment by again referencing words, some of which are four elements apart, and some of which belong to the same block. So in this case, after the first miss, the fourth element was in the RAM. Uh, the fourth element was brought into the RAM, and its corresponding four elements around it. Now the fifth element was also brought into the cache, so it produced a hit, and after that eighth element was not in the cache because it is a four element part or more than four element part from the previously fetched element, so it created a mess, and after that an element which was within the bounds of four element was referenced, which created a hit. So this way I simulated an environment where there are half of hits and half of misses. Now we'll be moving towards fully associative mapping scheme and demonstrating the same situations as before. Now for this fully associative cache, I will be running this command which will simulate all hits in a cache. Now let me just copy this command and paste it into my terminal, and now there isn't much difference as before, but there is one noticeable change, which is that there are none index bits now, and the number of tag bits have increased. So why are there no index bits? Because in a fully associative cache, we have also referenced the number of blocks per set are now 64. So as I was saying, in a fully associative cache, there are only a single set and all the belong there is only a single set and all the blocks belong to that single set. The number of blocks per set, so we have a total of 64 blocks and a single set. All the 64 blocks are present inside of that single set, so we do not need index bits to reference a set. But we do need tag and offset bits. Of course, within a block, there are four words which need to be referenced. Just like the previous example, I use the same addresses, which creates a scenario of all the hits in a cache. The second scenario in a fully associative cache is all misses. Now I will be just copying this command, and here we can see there are all misses in a cache, and because of these memory addresses. So the memory addresses are same as before, uh, because the associativity has no effect on the number of hits or cache, but we have some differences. There are differences like the number of blocks per set have changed. There are no index bits now, and the tag bits have increased. Now, this address, just like before, created a scenario in which there are all misses in a cache because the elements fetched are four words apart. Now, as we have seen before, when the zeroth element is fetched, so the corresponding four elements, which are 0, 1, 2, and 3, are fetched into the cache. But in this case, the next element referenced is four words apart, so again it created a miss in a cache. And now I'll be running this command, which will simulate an environment in a fully associative cache scheme, which will produce 50% hits. Now let me just copy this command. And just like before, we can see that I have used 11 addresses, and aside from the first one, all of them will be exactly and there will be exactly 50% hits and 50% misses. Now I'll be moving towards the next cache scheme, which is two-way set associative. Now the difference here is that each set will contain two blocks, which is indicated here by the argument number of blocks per set. The rest is, I guess, the same. So I'll be running this command and we'll see what is the output, what the output is generated by the simulator. Now, after running this command, the major difference we see is the number of indexes are now back, and there are 5 bits used to reference and index. What this tells us that if we run 2 raised to power 5, we have 32. This indicates that we have 32 total sets, and each set has 2 blocks within it. So 32 into 2 will produce 64, and there are 64 total blocks, and if we do 64 into 4, which will produce 256. So in this way, whole of the cache is referenced. So the index will be used to identify which set within a cache contains the element. or will be used to reference an element. And offset, of course, will be used to reference an element within a block. So here, just like before, I have used the same memory addresses to simulate an environment in which there are all of hits in a cache, because of these elements and the way these elements are brought into the cache. Now moving on, I'll be running the example which will produce all misses in a cache. And we can see that this particular chain of memory addresses produces all misses, and there are some differences in the index as well. The index is used to identify the set within cache. So here we can see that each of the element is then mapped to a different index value. So as because none of the elements created a hit, so each new element brought into the cache, and each new block of elements brought into the cache are saved into the corresponding set corresponding to these addresses, which are referenced by the index bits. So now moving on, I'll be running a scenario where there are 50% hits using the addresses as same as before. If I use these addresses, and just like before, they create a situation where there are 50% hits and 50% misses. And looking at the index, we can see then after the first element, after the second element was brought into the cache, and afterwards, when the third element here, which is 5, was referenced, the indexes are same. So it means that both of these elements belong to a same set, and within the blocks and within the block, they have different positions. So one is at 0 0 position, and second one is 0 1 position, but both of them belong to the same set. Here is a tool that I want to demonstrate, which will help visualize this. Yeah, here I have a two-way set associative cache scheme, and I have set these values according to the simulator I was using here, the command line simulator. So I have a cache size of 256, and I'll be referencing a memory of 2 raised to power 11, which is 2048. As we have seen that the number of bits used to reference a memory I have used here is 11, which doesn't make any difference for this simulator, as it does not address the memory referencing part, but here it has much better meaning to it, and the number of offset bits are 2. So here we can see, just like in a two-way associative scheme, in this simulator, we have 5 index bits, 4 tag bits, and 2 offset bits. Here the same is given: 4 bits for tag, 5 for index, and 2 for offset. And with that, we calculated that there will be a total of 32 blocks. So here we can see, starting from 0 up till 31, there are total of 32 blocks. And there are total of 32 sets. I mentioned blocks, instead of sets. So there are total of 32 sets, and there will be total of 64 blocks. Uh, uh, and now if I go to fully associative cache tab and put in the same values, we can see that there are 9 bits for block and 2 bits for offset. Uh, Now in our command line simulator, we will verify that. So we can see that in there are in fact 9 bits for tag, and the 2 bits for offset and none for the index. So here we can see that there are a total of 63, or should I say 64 blocks in this case, because all the blocks belong to a single set in a fully associative cache scheme. Now I will be going to our direct map cache and put in the same values, and we could see that here there are 3 bits for tag, 6 bits for index, and uh, 2 bits for offset. So in a direct map, each set contains only one block. So here we can see that there are 6 bits to index or to reference set. So if we do 2 is to power 6, it creates 64. So the number of blocks and sets are the same in our direct map scheme. And that will be all for now. Thank you.